Hello everyone, this is a class of ECE341, the probability and random process. Welcome. The last time we have discussed the probability and we have do some examples, try to estimate the probability by repeat the experiment and take account how many times certain event happened or not, then we can use that number divide by the whole amount of experiment. Use that way we can estimate the probability of an event. Okay, now we consider another side. Just suppose someone told you, so he has a coin. That coin has 0.6 as a probability to get face, and 0.5 of the probability to get tail. Is that good? Oh, you are saying one side you have chance 0.6, another side you have chance 0.5. Is it good? Now you are saying no, right? You totally 100%. One side you have 60%, the other side 50%. No, it's impossible, right? The totally together should be 100%. Now totally is 110%. So this is not right one. This is not a good distribution of the probabilities. So we need actually we need some laws or some rules to distribute different number, different probability to different events. So some kind of probability you think okay, it's good, but some different way to distribute the probability might be wrong. So we need some rules. So okay, so this is what we will study today: the law, some axioms, some theorems about the probability. ECE341, the probability course. This is actually the fourth class, right? And we will consider first one is axioms of probability. So axioms, that means some you think fact, some statement that is you don't need to prove it, you just believe it will be, it is true, it is truth, it is correct, right? We suppose we have an experiment, we have a random experiment, right? A random experiment with sample space S, capital S, sample space, and the probability we write it as P, and I write in this way. Here this dot means any event of this experiment. The event will be a subset of S, part of S, right? Okay, then we call it axioms. Axiom 1, the probability of any event A must be a number non-negative for any A. A is a subset of S, or maybe equal. The S itself is also an event. So for any event, it's an event. For any event A, the probability of A must be a number non-negative. Right? This is we don't need to prove it. We just know to the possible. The smallest possibility will be 0. Right? Probability will be 0. So it will be larger than or maybe equal to 0. Yeah.
and the other side, the probability of the whole sample space, there will be 1. That means, yeah, 100%, right? We use 100% to describe the case that is always happen, right? Always happen. So this is a 1. The largest probability is 1. And axiom 3, if we have some list of events for events A1, A2, A3, the list, there's a lot, infinite. If AI and AJ, for the intersection of them, they are empty, for any different one, you pick any different 2 events from this list of events. If they do not have intersection, then the probability A1 union A2 union, the union of all these events, you check the probability, and the other side you calculate the probability of each event, then do a summation. Okay, these 2 numbers, they are same. Make sense? Yeah, you have several events. They do not have intersection. Then the probability of all of them is a summation of the probability of each event. Yeah, makes sense, right? Okay, so all of these 3, they are true, right? People believe they are true. No problem. It is true. But they are true. And other than these, actually after these, based on these 3 axioms, we can prove some more, like we can say formulas or statements related with probability. Okay, let me list all of them. Now, theorems. The first one. This is the first one for the axioms of probability. Now it's the second part is the theorems. Theorems of probability. Actually, these theorems, they are also something similar with these axioms, and you can understand it. Yeah, very easy. You know the meaning. But these theorems can be proved based on these axioms. Yeah, what do we mean axioms? What do we mean theorems? The difference is here. Axioms, you don't need to prove it, and actually you cannot prove it. This is just we stated it. We give a statement here, and we know, okay, they must be true. You cannot prove it based on something. And the theorem, you can prove that based on the axioms. Yeah, you start from axioms by some logic reason, then you can prove, okay, we have theorems. Yeah. Now let's see. Theorems. What kind of theorems do we have? Actually, you can check the textbook. All these theorems, they are listed in the textbook, and here I just go over them. Theorem 1 in the textbook, maybe like they have 3 numbers, which chapter, which section, which one, right? They have 3 numbers. Here I just say theorem 1. Okay, theorem 1. Now we consider this one, the probability of a union of 2 events. 2 events, just 2. Similar with axiom 3. Axiom 3, we have a list of events, right? Now we only have 2. Then this one will equal to probability of A1 plus probability of A2 if A1 intersection with A2 is the intersection of A1, A2 is empty. Yeah, actually this is just axiom 3, but you restrict only contain two of them. Then you have two events, they do not have intersection, then the probability, the union's probability equal to the summation of the probabilities. The probability of the unions equal to the summation of the probability. Yeah, so the same thing, right? To prove is also easy. You just suppose A3, A4, A5, all the rest of those A's, they are empty. Then you can have it, right? You can have 0 and 1. Okay, so this is 0 and 1, and 0 and 2. The similar thing. I just give more. So here, PA1 union union A2 union until AM. This one equal to the summation of all these A's. Probability A1, A2 to summation until probability of AM. I have okay, now just to fit. Right. You see? Yeah, the summation of the probability of each event. And suppose we need condition AI intersection with AJ is empty for I do not equal to J. So this is 0 and 2. Similar with 0 and 1, just we have more events, right? 0 and 1 we have only 2 events. Then 0 and 2 we can consider we can have like 3 events, 5 events, 1,000 events, but a finite number of events. In axioms, in axiom 3, we have, you can say it's an infinite event, right? Infinite, yeah, no, it's endless, right? Okay, so here's finite. This is the second theorem, and the third one. The third one, now we consider the event which only contain one symbol, right? One symbol. If B equal to S1, S2 until SK, then each SI is an symbol in symbol space. Is a symbol, sorry. It's a symbol in symbol space. Right. Just one symbol. Right. Each SI is one symbol in the symbol space. Then the probability of B will equal to probability of S1 plus probability of the event S2. And writing this way, that means this is an event, right? An event only contains one symbol, and the probability of this event. Alright. The summation until last term is probability of the event SK. Yeah, we have this one. Actually, this is a special case of this theorem 2. Okay? This is theorem 2. In theorem 2, we consider M, right? We have finite number of events, but each event may be varies, right? Because it may contain different kind of symbols. And in theorem 3, now B is a union of these events. Each event only contains one symbol. Right? So this is the theorem 3 is a special case of theorem 2. That is the case each AI just contains one symbol SI. Okay. Theorem 3. Yeah. Then theorem 4. Yes. Theorem 4. Oh, is this one? Now we consider this is B, right? This is B as this is an event. This is an event. This is event. And now we consider whole sample space. The sample space S contains finite samples. So n samples. Right? Suppose this is S, sample space. Remember, we have examples on the sample space. Some case the sample space contain infinite samples, right? And sometimes they only contain finite. Like the dice, you have 6 samples. A coin, you have 2 samples. Right? Yeah. So suppose S looks like this, and each Si, each small sample Si, each Si, they have, each one is, I would say they have same probability, equal likely, right? Equally likely to happen. Yeah. Yeah, equal likely to happen. Yeah. Then the probability of each Si will be just 1 over n. That's it. Yeah. If you want to give more details, you can write in this way. Yeah, it's the total amount of elements in the sample space, right? 1 over that. 1 over that. It's 1 out of n. That is the probability of just one numbers. We have samples, right? Like the dice. You check the dice. You roll dice. Then each number you will have 1/6 probability, right? Totally 6 numbers. 1/6, 1 out of 6. Yeah. So this one we have 0. Actually, all these 0, 1, 2, 3, 4 is kind of things. You just think about it. This it will be this, right? But here I say they are zeros because all of them they can be proved through those axioms. You start from axioms, then you can prove this one. Yeah. Okay. This is theorem 4, theorem 5. Sorry, theorem 5. So we have this one, an event with a C. This is a complement of A. Remember, complement of A. This one will equal to 1 minus PA. Yeah, things like that. This is a whole sample space, and we have the event A. Then the complement of A is the outside AC. Right, the AC. So the probability of AC is 1 minus probability of A. And of course, the probability of S is 1. Then we have empty. The empty, it is just the A complement. Right? A complement is empty, and this is 1 minus 1 equal to 0. Yeah, this is special case of the first formula. So this is also 0. We have this one. We have this one. When you want to calculate the probability of AC, that is just 1 minus probability of A. So like you use a dice, the probability dice, then the probability of no 1 is 1 minus, actually not 1. The 1 minus 1/6 is 5 over 6. Right. You check the result. Your result is not 1. That is the event. Then the complement, it is a complement of your result is 1. So the probability is 1 minus 1/6. You get 5 of 6. It's 0.5. And alright, this one will be a little bit looks like a large deal. It is probability of A union with B equal to probability of A plus probability of B, but minus the intersection of probability of event A and B. Alright, this one we can compare this one with 0, 1, and 2. In 0, 1, you have two events. You check the union, the probability of the union equal to the summation of each, right? And here similar, the union of A and B, the probability will be summation of each, right? The summation of the probability of each, and minus the probability of the intersection of the. So we have one more term other than 0 and 1. Where did it come from? Actually, this is come from the intersection, right? In 0 and 1, the intersection is empty, so no intersection. So here we do not need the rest part. But now in generally, for any A and B, if they have intersection, then you need to minus these to calculate the probability. Yeah, makes sense? We can use a graph to see. There you have S. Okay? Suppose this is A, this is a B, and here's the intersection. Okay? So when you calculate PA, right, this side, then PB is this side. So the summation of PA and PB, it contains this part 2 times. Right? When you calculate PA, you have this part, and when you calculate PB, you also have this part. So when you calculate, you do this summation, you take account this part 2 times. So you need to you remove one of it. So remove one of it, you minus P of A intersection with B. So after this, you get the probability of A union with B. Okay, so this is the result, right? It's 0 and 6, 0 and 6. All right. Then 0 and what else do we have? I have this one. If A is a part of B, then the probability of A will be a number smaller than the probability of B. Yeah, obviously, right? This one is kind of, if you want, you can also use this one as an axiom. I think in some probability books, this one is also is given as an axiom. That doesn't matter. Doesn't matter. We can just have this. Yeah, we can prove it based on axioms. Of course, I don't prove it here. If you are interested, you can read the textbook, or maybe you need to read some textbook of probabilities for the math department. They get more details and prove everything. In our textbook, I think most of the theorems, they just give some illustration. Yeah, no proof. No proof. You just remember them, then you know how to use them, they will be fine. Okay, this is 0 and 7, and we have more, I think. 0 and 7, 0 and 8. Yeah, we have 0 and 8, which we can separate the sample space. 0 and 8. Like if we separated the whole sample space as event space, what will happen? Suppose you say B1, B2 until some Bm is a event space, is an event space. Event space. Then for any event, we calculated the probability of this event or equal to probability of A intersection with B1 plus probability of A intersection with B2 until the probability of A intersection with B. Yeah, so like this. This one is similar with the previous theorem. Let me see. Yeah, theorem 3. 8 and 3. Of course, the notation is a little bit different. The thing like this. This B1 to Bn, they are some kind of things you think. Now here's S1 to Sk, right? S1 to Sk. Now they are, we separate the sample space as event space. So those S, some of them will combine together as B. So they are these kind of things. B1, B2, Bn, right? Yeah, the A's. In this one, you want to calculate probability of B. You check every element in B, then find the probability of each event, each sample, do summation, right? B, they check all the samples in B, find the probability of all the samples, do summation, you have B. Now is A. A is a combine of those, not samples, those intersection with B. So like A intersection with B1, this will contain the samples inside B1, not just one sample. Maybe you have several samples, right? Several samples in B1. Yeah, several samples in B2. And then you calculate the probability of this part, probability of this part, then do the summation, you have the whole probability. Yeah, things like that. Similar with theorem 3. But this is in the event space. This is in the sample space. A, and let me see, what else do we have? Yeah, I think that's all. You check the textbook. That will be in the textbook section 3 and section 4 of the 3 and 4. Yeah, I will give the number of the sections and the listing in the black box. Alright, so you should know which part you can read and which part you can find all these theorems. Alright, now let's consider an example. Study an example. We consider this. We consider like the code, binary code of 0 and 1s with length 3. Right, so 3-bit code, 3-bit binary code. Right, this one. This 3-bit, we have different meaning related with, like bit 1, bit 2, as B is B, yeah, B1, B2, B3. B1, we can have value 0 and 1, and we consider 0 is negative and 1 is positive. So we consider the meaning of 0, 1, they are sign of the number, and these two, there will be number between 0, 1, 2 and 3, right? 2-bit. Then we can have numbers 0, 1, 2, 3. I write this as like X. So the result, the possible result of these 3-bit binary code, the meaning can be like this. For X, we can have 0, 1, 2, 3. And for B1, we can have negative or positive. So totally together, we put them together, we can have negative 0, negative 1, negative 2, negative 3. positive 1, positive 0, positive 1, positive 2, positive 3. So we have these at a sample space. This is sample space. You can write as equal to positive or negative I. I can be 0, 1, 2, 3. But here you should mention negative 0 and positive 0. Here they are different code. They are code, not really numbers. They are different code. You can understand these codes. You think positive and negative zeros are same number, but as a code they are different. As code they are different, right? So these are sample space. Now we suppose you have a kind of you have this kind of code. You obtain the code from some resource like internet or some files or something. Then by your observation, you can have a probability, some kind of probability, right? But the probability number, it is not full numbers. You have some of it, things like that. Suppose we obtain some estimation of the probability of some part of S as this. As here use this is a X, this is a B1, positive, negative, negative, positive. X will be 0, 1, 2, 3. Then I give numbers here. This one I put 0.1. This is a probability, 0.1. And we do not have these. We have this is a 0.2. And we have here is 0.4. So what is meaning? 0.4 is a probability of negative, right? The whole row, you do summation together, should be this one, 0.4. And for this line, I have like I don't know, like 0.2, suppose, and the point. This is also 0.2. Okay, 0.2 and 0.2, and then here we have the 0.3 and 0.25. All right. Suppose we know these. Okay. This is probabilities. Probability, right? Okay. Then can we find all of them? Right? We have so many things we do not know. Can we find them? Actually, this problem has two parts. One part is whether these estimations are correct. Yeah, maybe your estimation gets something wrong, right? It's estimation, not so accurate. Sometimes maybe you have something wrong. So you will check whether it is a right distribution of the probability, right? This kind of distribution, totally 100%, totally is 1. So here's 0.1, 0.2, 0.2, 0.2, and 0.4, 0.25, 0.3. Then what will be the rest? Now, it's a kind of distribution. So whether this distribution is a good distribution for probability. Yeah. And if it is a good distribution of the probability, what are these numbers? So we have two questions. Okay. Whether this is a correct one, right? Distribution of probability. secondly, if it is correct, what are the full description, I just say. Full description. We want to know all the probabilities, right? Now we already have part of it. Okay, then we can do the work just based on those theorems. I gave some notations here. I gave I guess some unknown thing, right? I say this is x1, x2, x3, x4, x5, x6, x7, x8. We want to find we have 8 unknowns. Can we get it? Yeah, we can just try. Then we should use the theorems and axioms of the probability. So let me see. Yeah, we can check the first row. First row, the totally summation of the probability should be 0.4. This 0.4 is the probability of b1 equal to negative. X could be any. Right? So the summation 0.4 should be summation of these 4 numbers. So we have 0.1 plus x1 plus x2 plus 0.2. This is 0.4. Can we get something here? No. Yeah, we can have something. X1 plus x2 should be 0.1. Should be 0.1, right? But this is not enough to determine that. We can check the second line here. So we have 0.2, 0.2, 0.4, okay. So what is 0.5? You see, B1 either negative or positive, right? Negative or positive. So negative has probability 4. Actually, x5 equal the probability of B1 equal to positive. This is a probability of B1 equal to negative with a complement. So it is 1 minus 0.4, which is 0.6. So x5 must be 0.6. Yeah, we already get 1, right? x5. And actually x8 should be 1. Should be 1 equal to x4 plus x5. No, 0.4. This is 0.4. I'm sorry. 0.4 plus x5 equal to, that is a point. Should be 1. Right? 0.4 plus 0.6. We have 1. This is x8. We have second one. Okay, we have these two. Then we go to this side. 0.1 plus x3, there will be x6. x6 is the probability of 0. b1 could be any, x should be 0. So we have, this is x6. Well, so far this one we cannot do any final result. Let's check the second. This is this column. Okay, x1 plus 0.2 equal to 0.3. Okay, this one gives us a result. We have x1 equal to 0.1. Right? Okay, we have x1. Oh, then we can have this one, right? x1 is given. We have x1 is 0.1. Oh, so x2 is 0. It is 0, right? Am I good? Yeah, this is 0. x2 is 0. Okay, we have x2. Then what else can we have? Can we plug this here? No. Alright, now we check the next column. Is x2 plus 0.2 equal to x7. Alright, x2 is 0, so x7 is a 0.2. Same with 0.2. Okay, we have x7. and then x4 plus 0.2 will be 0.25. Okay, so we have x4 equal to 0.5. x4 equal to 0.5. Then anything good? We can have don't know what else do we have. Okay, I list the result in a table way. In a table way, here's a 0.1, 0.2, 0.2, 0.2, 0.4, and we have x2 is 0, x2 is 0, and x5 is 0.6, and x1 is 0. Yeah, x2 is 0, x5 is 0.6, then x8 is 1, then x1 is here, is 0.1, and x7 is 7 is here, 7 is 0.2, and x4 is here, 0.05, sorry, 0.05, and here's a 0.25. 0.25 is given. This is 0.25. I use black for the given number and the red for the number we found, right? So this way I get 0.4. This way I should get 0.6. Okay, so here's a 2, 2. So here I need a 0.15, right? 0.15. 0.15, then we have 0.6. Then I have x4, yeah, I have x7, this is this one. Then here x.3 is given, this is 0.3 is given, right, 0.3 is given. And this number, summation of these two is 0.25, okay. And if we do summation along this way, this also give us 1, right? 0.25, 0.3, 0.2, 0.25. So it's 5 and 5 is 1. Okay, now it's good. So we have the final answer, looks like this. The probability, the sample space is here. Yeah, sample space is here. We have 8 different results, and then the probability of each, they are 0.1, 0.10, 0.2, 0.15, 0.2, 0.2, 0.05. We have this part. This part, they are the probability of each sample, right? Each sample in sample space, we have the property like this, and we have the boundary, right? The marginal. We have here these 2 and these 4. Actually, we have names for them. We call these. We have different. Okay. We have these and these. Because this is a marginal distribution. Yeah. And this part called is a joint distribution. we have these kind of things when we have the sample space in like a two-dimensional, two-dimensional. Like here, we have the sample space, right? We have two-dimensional. One dimensional is for the sign, negative and positive. The other dimensional is the numbers 0, 1, 2, 3. So the sample space, if you give it like listed as a tables, you can see this is like a two-dimensional, right? Two-dimensional, two directions, two-dimensional. So in this case, when you want to find the probability, we have these kind of names. We call this part, each is a probability in that two-dimensional sample space. We call this a joint distribution. Right? You distribute those 100% to all these places. Right? This is a joint distribution. Joint because we have two for the sample space. Right? One is a 0, 1, 2, 3. The other side is a negative, positive. So it's a joint. It's a joint of the factor. Joint of factors. So joint distribution. And this side we call the marginal distribution. They are the summation of the joint distribution. Like you do summation along this row, you get this number, right? 0.4, the summation of all these four numbers, and 0.6, the summation of all these four numbers, and this 1 is also summation of these four numbers. So this is one margin, right? This is a whole, like a whole plate. This is a margin, and this is another margin, another direction. Each number is summation of the column. Like here, 0.25 is summation of these two. This 0.3 is summation of these two. Right? This is marginal. We call this marginal distribution. Marginal distribution. You will distribute this 1 into each margin. Right? Here's 4 and 6, 40 and 60%. And here's 25%, 30%, 2%, 25%. Right? You have different direction you do the distribution, and each one you also distribute along the row and the column. Okay, this 4 distributed along this row, and this like 0.25 distribute to these two numbers, 0.1 and 0.15. The rule is you need to make summation equal. Along this row do summation, you get this marginal number. Along this row do summation, you will have this marginal number. And along every column do summation will equal to the number in the margin, in the marginal, right? Yeah. So this related with the feature here, we have the probability. Actually, you can think they are all come out from the axioms, right? Yeah, and maybe like this. The summation of two events. This is the probability of each do summation. This is the union, then do summation, then do probability, right? These two. So like this one 0.4 is the probability of negative. It will be a summation of all these 4 cases, right? Union of these 4 cases. 4 cases, each one with probability like this. So the overall probability will be summation of that, right? So this is according to theorem 2 when m is 4, right? And when you check the column, actually this is according to theorem 1, right? 2 event do union, right? So these 2 you do union, you get this one. And last one is you do summation along this row or along this column in the marginal. Then these 4 events you do union, you get whole sample space. Then probability you do summation, you get 1. The same here. The event union, you get whole sample space. And the probability to summation, you get 100%. Yeah. All right. Okay, that's all for today, and
see you next time. Bye bye.